I want to take a look at our two op-amp circuits and make an interesting observation about how these things are behaving when they are working properly. When they're hooked up right, there's something these things do that is really helpful and makes life simple for us. Let's let the gain of our op-amp be 10 to the third or 10 to the sixth, really high gain, a million. And we're going to let the output voltage here, V out, let's say 6 volts. And you remember what's not shown here in this circuit is the power supplies going to both of these op-amps, plus or minus, let's say it's plus or minus 12 volts. Those power supplies are implicit. They're not shown in the diagram, but we know they're there. All right. Now, if V out is 6 volts and A is 10 to the 6th, then what's V in? V in is the difference between these two voltages here. Let's call this the usual thing. We'll call this V plus, and we'll call this V minus. And we know that V in equals V plus minus V minus. And now what the question is, what is V in terms of V out? Well, V in equals V out divided by A. If we fill in the values we had, it's 6 volts divided by 10 to the 6th, or 6 microvolts. So this is 6 microvolts between here and here. Okay, so with 6 volts here, there's 6 microvolts over here. Okay, this is a really small voltage. In order for this op-amp to have an output voltage that stays between plus or minus 12 volts, this voltage over here has to be really small. It has to be down to the microvolts level. So because I'm a practical engineer, I'm just going to say this is pretty much 0 volts. And if I say this is 0, that's pretty much the same thing as saying that V plus approximately equals V minus. So that's a little observation we're going to make right there. So in this circuit, when it's working right, these two voltages are pretty much the same. So let's take this idea V plus pretty much equals V minus and apply it to this circuit over here. Now this is our inverting configuration for an op-amp. So this is V plus and this is V minus in this circuit. And let's do the same analysis that we did before. If this is V out, and if V out is 6 volts, that means that V plus minus V minus divided by 10 to the 6th equals 6 microvolts. And that says that this is 6 microvolts in this direction. When we did this over here, because the signs of the inputs are flipped, this was 6 microvolts this way. So again, because of the enormous gain of this amplifier, this is always going to be a tiny, tiny number. And so, heck, why not make it 0? So if I treat this as 0, what it means is I'm going to go right in here, and I'm going to change this to 0 volts. So let's make a couple of more observations, okay? Right now it says right here, V plus equals 0 because it's grounded. So what does that mean V minus is? Well, V minus is also 0. V minus is 0. So that point right there is at 0 volts. Okay, so that's pretty cool. So that point's at 0 volts. Now, is it connected to ground? It's not connected to ground, but it's 0 volts because of what this op-amp is doing for us. This op-amp is making sure by this feedback path that this node is always next to this node, and that means it's always 0. There's a really cool word that we use for this, and the word is virtual. And what does the word virtual mean? Well, virtual means that something is not there, but it seems like it is. So in this case, this node is not connected to ground, but it seems like it is. So this is referred to as a virtual ground. So these two ideas say the same thing. V plus equals V minus is always the situation around the input to an op-amp when it's running properly. And in the case particularly of this op-amp configuration where the plus terminal is connected to ground, we say that the other terminal, V minus, is at a virtual ground or is a virtual ground. In the next video, I'm going to go back and do this inverting configuration of the op-amp. I'm going to do the analysis again with this idea of a virtual ground, and it's going to be really easy compared to doing all that algebra.